Good afternoon. I welcome you all in this session of fluid mechanics. Well, we are discussing the continuity equation and deduced the equation in different coordinate systems, Cartesian coordinate system and also in cylindrical polar coordinate system. Well, let us see the equation that if we recollect, the continuity equation is del rho del t plus divergence of rho into velocity vector. As we recall, this was the differential equation, or this was the equation for continuity. That means the statement of conservation of mass applied to a control volume. And what we have found out, that by expanding this in different frame of reference, whether it is a Cartesian rectangular Cartesian coordinate system in conventional x, y, z like this, x, y, z, or in a cylindrical polar coordinate system or even spherical polar coordinate system, we can derive different form of the equations or equations with respect to different coordinate system. And another way of deriving it is to use the fundamental principles of conservation of mass to a control volume of fluid appropriate to the coordinate system. So in any case, this general equation in vector form is the differential form of the continuity equation. Since this is a differential equation, you see this is a differential operator. So this is known as differential form of continuity equation. Differential form of continuity equation. So this gives the differential equation. So that's why it is known as differential form of continuity equation. Now today we will find another, or we will deduce another form of continuity equation, which is known as integral form. Integral form of continuity equation. That means continuity equation. Continuity equation means the same, that is equation derived from the same principle of conservation of mass applied to a control volume. So that is the continuity equation by its physical significance, and this continuity equation integrated form. Integrated form. So earlier we discussed the differential form, now integrated form. Very simple. Let us consider a finite control volume like that. So to derive the integrated form, we don't require first any frame of reference, just we consider a control volume of an arbitrary shape whose total volume is V and which is bounded by a surface area A, bounded by a surface whose surface area is A. Now let us consider the mass flux like this. Let us consider the mass flux. This is the mass flux which crosses the control volume. Let us consider these are the mass fluxes, crosses the control volume. This is the mass flux, mass flux. So we define a control volume in a flow field where the mass flux crosses the control surface. You know the boundary of the control volume is known as control surface. This is the control surface, control surface. Now if we find out, now first of all, we have to find out the total mass efflux and the rate of mass increase in the control volume. Now if we specify a small elemental area dA on the control surface where the velocity vector is V, this is the velocity vector at this point enclosing this small elemental area dA, then we can tell that the mass efflux from this elemental surface dA is what? Which is V dot, that is V is the velocity vector, dot NdA. What is this? This is the mass efflux. I am not writing everything, I am telling that mass, if this quantity represents the mass efflux from this area dA. What is the N? N, this N is a unit vector in the direction perpendicular to this area element dA and taken positive when directed outwards from this area. So that means dA is the scalar magnitude of the area, and this is multiplied with an unit vector to give a vector sense of it, where unit vector is along the perpendicular direction and taken positive when directed outwards. So physical significance of this means that the cross-sectional area and the velocity of flow normal to this cross-sectional area. As you know, to find out the flow across any section, we multiply the cross-sectional area with the velocity of flow perpendicular to this area. This is expressed by this dot product in vector form. So now if we integrate this over the entire area of the control volume, that means the entire area bounded by the control surface, then we get this as the net rate of mass efflux from the control volume. So I can write this as net rate of mass efflux from the control volume, from CV, control volume, the total area. Now here if we consider an area, there is a mass influx. How it is indicated? This is because in that case V, the velocity vector, and this, for example, this is the normal direction outwards, which is taken positive outwards, very important. So that this will be in the opposite direction, so there will be a negative sign. That means if we integrate this over the entire surface area depending upon the mutual direction of velocity vector and this vector in the net efflux will be determined like that. That means efflux minus influx, which will be taken care of by the entire surface in this way. So mathematically one can tell that V dot n bar dA, n dA, where this n is an unit vector as I have defined, is the net rate of mass efflux from control volume. Okay, rho, very good, rho should be there. This could have been the volume efflux. Very good. I am sorry, very good, it is rho V n dA. So rho should come because otherwise this is the volume flow rate. So net rate of mass efflux. Now what is net rate of increase of mass? Net rate of increase of mass in the control volume, this is very simple. If we take, for example, at a point where the density is rho and a small elemental volume dV enclosing that point, then rho dV is the mass at that point. So simply we tell that it is the integral of rho, because rho is varying, rho can vary within the control volume, so simply rho dV over the control volume. All right. So therefore we can write according to our statement of conservation of mass applied to control volume, if you recall, and it is very simple, from very simple physical intuition, that the net rate of mass efflux from control volume plus the net rate of increase of mass in control volume is 0. That means we can write that this as the first term dV plus the net rate of mass efflux rho V. This is one vector and this is another vector. So this is the general form of the continuity equation in integral form. So this is the continuity equation, integrated form or integral form. This is the general expression. Now you tell me that, I am sorry, this is the rate of change del T. Del T of rho, so there will be a del T term. Del T of rho dV, I am sorry, del T of rho dV. So this can be written, of course, with another, because since the volume dV, del T of rho dV, we can write this way, that this should be the total volume del rho del T. So del rho del T to dV, well, plus it is this, okay, rho V dot as it is. I am sorry, that, so this is the volume integral, this is the surface integral. Triple integral. This is all right? Okay. So this is the, okay, I am sorry, triple integral. This is the integral form of the continuity equation. Now, you tell me under steady condition what will be happen for steady flow? For steady flow, what is this? Steady flow, this will be 0. So for steady flow, the equation is, here I write surface integral rho V dot dA is 0. And for incompressible flow, whether steady or unsteady, incompressible flow means density is constant. Incompressible flow, what will be this term? That is over the area. Incompressible flow also, this will be 0, and moreover rho will come out, because rho is invariant in this entire control volume. So rho will come out. So simply for incompressible flow, surface integral, V dot 0. That means it is the volume flow rate which is conserved. Simply physically in a compressible flow, mass flow rate is conserved, and for incompressible flow it is the volume flow rate that is conserved. Now for a steady flow, this is the equation. For incompressible flow, this is the equation. So this is a vector form. Sometimes it is difficult to recognize physically. So from engineering point of view, simply you can guess this way. Let us consider a channel formed by two streamlines. Formed by two streamlines. These are two streamlines. Sometimes we describe a stream tube. It is a tube formed by different streamlines. That the surface of the tube is the stream surface, whose cross-sectional area is a circle. But we can think of a channel also, which has got some depth in this direction and which is bounded by two streamlines. So in that case, if you think from two-dimensional point of view, see that if we define a control volume like this, for example A, B, C, D, then in this case the flow only, let us consider the velocity vector is such that it is like this. So mass flux only crosses the control surface or comes into the control volume, this formed by these two streamlines, across the surface AD and across the surface BC, because this surface or this line across which there will be 0, that means 0, no mass flow, by definition of no mass flow, by definition of this streamline. So now if we tell that this cross-sectional area is A2 and this cross-sectional area is A2, this is A1, and if we tell the velocity vector normal or velocity normal to this area is V1 and velocity normal to this area is V2, then this equation simply tells if rho 1 is the density here, rho 2 is the density here, the integration over the entire control volume will simply yield rho 1 A1 V1 is equal to rho 2 A2 V2. Okay. So this is a very simple case that when in case of flow through a pipe, if we consider the inlet section of area A1 where the velocity is V1 perpendicular to the cross section, then rho 1 A1 V1 is the mass flow coming in. So we don't go through all these detailed equation from simple physics or physical concept. We tell this is the mass flow coming into the control volume. For example, in a pipe there is no flow across the rigid boundary. That's why a rigid boundary always behaves like a control surface or as a stream surface or streamline, because across which there is no mass flow, and that must be equal to that going out, rho 2 A2 V2. In case of incompressible flow, it is A1 V1 is A2. That is very simple consequence of continuity. That means the volume flow rate which is coming in to the control volume must going out to the control volume. In case of incompressible flow, it is the volume flow rate which is conserved, while in case of compressible flow, it is the mass flow rate which is conserved. Well, I think this is clear. Now we will switch on to the next section, momentum equation. Now what is momentum equation? So far we have derived the continuity equation, that is the conservation of mass applied to a fluid flow system, and we have considered the control volume approach, that we have considered a control volume where the conservation of mass we have applied, that is the very preliminary and fundamental conservation statement, and we have derived the continuity equation. Now one thing we have seen that in deriving the continuity equation, rather while applying the conservation of mass to a fluid flow, the concept of viscosity or question of viscosity does not come into picture. Why? This is because no force is coming into picture, it is only the flow of fluid. So when the flow field is described, whether it is a viscous flow or it is a ideal flow, inviscid flow, doesn't matter. If flow field is defined, it has to satisfy continuity equation along with the density field to make a possible flow, because the conservation of mass has to be satisfied. Now we come to equation of motion. Now equation of statement conservation of momentum to derive the equation of motion for a fluid flow. Conservation of momentum. What is the conservation of momentum? The conservation of momentum, if you recall the principle of conservation of momentum applied to a system, that first consider the conservation of linear momentum, that is rate of change of linear momentum of a system is equal to the force acting on the system in the same direction. As you know, for a system mass is constant, so rate of change of momentum, that means mass into velocity, which is a vector, can be written as mass coming out. So mass into rate of change of velocity, that means mass into acceleration in a particular direction is equal to the net force acting on that system in that direction. The same equation of motion, that Newton's second law, which you have read in the preliminary physics, that is applied to a fluid system also. That means if you consider a system in a fluid flow of mass m, then this mass times into acceleration, if it is accelerated in a particular direction, must equal to the net force acting on that direction. So this is simply the momentum theorem or conservation of momentum, or you can tell the equation of motion applied to a system of solid or fluid as well. Now here one question comes, when you talk about the total force acting on a fluid body in a particular direction, you know there are two types of forces that act on a fluid system. As we have read earlier, we have discussed earlier, that one force is the external force acting on the fluid body, for example the gravitational force. There may be other external forces, some magnetic field in which the fluid flow is exposed, electrostatic field. These are the external force acting throughout the mass. Another force which is acting, if we take a fluid system in isolation, these are the surface forces which appear in the surface, contact forces. As you know, when it is taken as a free body in isolation from its surrounding mass, it is the action or reaction, as you the way you can think, that it is because of this mutual interaction between this fluid system with the surroundings. When it has been kept in isolation, these appear as the forces at its surface. So these forces are of two types. One is the normal force, another is the tangential force. So if the fluid viscosity is taken into account, all fluids have viscosity. So fluid with viscosity, the surface force yields to tangential forces also, apart from the normal compressive forces. As you know, in a fluid flow, the normal forces are only compressive forces, which is the pressure. But if we consider the fluid to be ideal, this is an hypothesis, this is a hypothetical situation. Theoretically, if we consider that fluid is frictionless, the way we consider a mechanical system, frictionless mechanical system, and we analyze it, though no mechanical system can be devoid of friction. Similarly, if we consider the fluid to be ideal fluid, that means zero viscosity fluid, then the only surface force is the pressure forces, that is normal compressive forces on the surface. So therefore, the shape of the equation or the form of the equation will change if we take viscosity or if we neglect viscosity of the fluid. So depending on that, the final expression which we derive from the application of the basic laws of conservation of momentum will differ. So firstly, in your syllabus, we will discuss the conservation of momentum, or the principle of conservation of momentum theorem applied to an ideal fluid, that is fluid without viscosity. And finally, the equations which will be derived by the application of this principle, we will see the velocity field, that is relationship between the velocity field and the pressure field, and the resulting equation is what is known as Euler's equation, because Euler was the scientist who first deduced this equation. That means applied the equation of motions, Newton's second law, to the flow of an ideal fluid. Let us see now Euler's equation. So if anybody asks what is Euler's equation, don't try to say Euler's equation, so du dt like that. You must say that Euler's equation is finally an equation relating the velocity and pressure field for an ideal fluid which is deduced from the application of the conservation of momentum. So now let us see that conservation of momentum, as you know, that mass into acceleration is equal to the force impressed on the system. Let us first consider the Euler's equation in a x, y Cartesian coordinate system Z, and let us define the fluid system like this. Compatible to this. Let us define a fluid system like this. A, B, it is a parallelepiped, as you know, A, B, C, D, compatible to the appropriate or compatible to the coordinate system. Now this is a fluid system now. Be careful, this is a system, not a control volume. There is the difference. And you will see afterward how the statement relates for both system and control volume. First of all, we are taking a fluid system because we are utilizing this expression mass into acceleration A in a particular direction is force in that direction. This is simply, as you have read earlier in school, that is the Newton's second law of motion. So therefore, acceleration only a system can have. Control volume may be fixed. Control volume may move with fluid, which will come afterwards, but control volume may be fixed, but it is system. That means the Newton's second law is basically defined for a system that will be modified for a control volume afterwards with the help of Reynolds transport theorem, which I will tell afterwards. So now we consider a system. System means which is moving in the flow, moving with the flow field. System has got a definite mass, so volume may not be constant, but mass is constant with fixed identity. You can think a system composed of different Lagrangian particles of fixed identity. That means system is a fixed mass with fixed identity which is moving in the flow, just like the Lagrangian particles move, because it is composed of Lagrangian particles of fixed identity. So therefore a system must have acceleration. So please think this is not a control volume as we did in case of continuity, because it is a system. Now in this system, let us consider these are the phases. What is the body, what is the pressure forces? First, surface forces acting on this, then what are the forces on this surface? If we consider the fluid to be an ideal fluid or ideal flow, whatever you call, flow of ideal fluid is the ideal flow, then the pressure forces, which is the only force acting here as P on this surface, AEHD. As you know, how do you define or specify the surface? The X surface. So the pressure force in another X surface parallel to it, BFGC, will be simply P plus del P del X into dx. Before that, I must define that this is dx. So this is dy, that means in y direction, this is the dimension of the system, and this is dz, that means this is dz dimension, linear dimension of the system. Neglecting the higher order term, we can tell the pressure is changed over a distance dx for these two planes, P plus del P del x dx. Extremely simple. Now if we define the pressure here on this ABCD plane, the y plane, then the pressure on the another y plane, which is separated by dy distance in the positive y direction, that means EFGH, will be P plus del P del y dy. My first job is to fix the force, because acceleration I know now from the kinematics. Similarly, if the pressure is P at, if we specify at this plane ABEF, then the pressure at another jet plane, that is DCGH, will be P plus del P del Z into dz. Dx, dy, dz are the dimensions of the system. So therefore, after recognizing these pressure forces, let us consider a body force acting on this system. Let we consider a body force like this, which is denoted by x bar at any direction. Let x bar is the body force per unit mass. As I have told, the body force is the external force which is acting throughout the mass, so it can be expressed in terms of the mass per unit mass. So body force per unit mass. X bar is the body force per unit mass, which can be written in terms of its component xx, xy and xz, in terms of its component in x direction, y direction, z direction, with I, j, k as the unit vectors in x, y, z direction. Now next task is what is m? M of the body is the system is the rho dx dy dz. Now if we write separately the equation of force, equation of motion, it is equal to m into ax is net force in the x direction. So m into ay is the net force in the y direction. Let us define in terms of vector. So fy in the, so m az is the net force in the z direction. So now you see what are the forces, net forces in x, y and z direction. What are the forces in x, y and z direction? So this, if you recall, ma, now let us see that. What are the forces? Just a minute to adjust this. Well, I think you can better can see this. So now, so if we now see this, now you see that what are the forces. Now if we recall that this m in x direction, ax is fx, m AY is FY, well, and MAZ is FZ. Now what is AX? AX is du dt. So if I write this for x direction, then I can write rho dx dy dz into du dt. What is the net force in the x direction? That is P plus del P del x into, that is this one first, P into dy dz minus P plus del P del x dx into dy dz. So net force in the x direction is P dy dz minus P plus del P del x dx into dy dz. Well, dy dz. Well, this is the net force. P into dy dz, you can see P plus del P del x into dy dz, dx into dy dz. This is the area plus the x component of x component of the body force. So therefore, this is rho per unit mass. This is the part, x bar nomenclature is the body force per unit mass. So mass times its x component. Alright. So if you make this, cancel dx dy dz from both these sides, you get an expression like this. Xx I take first, minus 1 upon rho del P del x. Okay, any problem? This is the x direction final equation we get by equating the forces. Similarly, if we do for this, Ay is dv dt, mass remains the same, and what is Fy? Fy is, let us write Fy. What is Fy? Fy is P dx dy, sorry, Fy is dx dz, P into dx dz minus P plus this force del P del y dy times dx dz, P plus del P del y, this is the pressure there, times dx dz. So this becomes equal to minus del P del y dx dy. That means in any direction, the net pressure forces either in x, y, z will come out to be the corresponding gradient. It was del P del x dx dy dz, it is del P del y dx dy dz. Similarly, if you consider the net forces in z direction, it will be minus del P del z dx dy dz. This is because in z direction P into dx dy minus P plus del P del z dz into dx dy, and it will ultimately yield to that. And if we use this as Fy and Ay is dv dt and Az is dw dt. So finally we get the same type of thing that we get for y component dv dt is equal to xy in consideration of the body force per unit mass, y component of the body force per unit mass, and dw dt is equal to xz minus 1 upon rho del P del z. So this is the x component, this is the y component. Alright, now again I write this thing. So therefore what we get in x direction, we get du dt. Equation of motion in x direction is xx minus 1 upon rho del P del x. Similarly for y direction, I write what is y direction, dv dt is equal to xy minus 1 upon rho del P del y. And for z direction, dw dt is equal to xz minus 1 upon, where P is the pressure in the flow, U is the x component of velocity, V is the y component of velocity, W is the z component of velocity in a typical xyz coordinate system, and xx, xy, sj are the x component body force per unit mass, y component of the body force per unit mass, z component of the body force per unit. About this we do not have any control from fluid mechanics point of view. This is described by the physics of the body force field. Now we can write this in a different form by splitting up this total acceleration. That means this can be written as del u del t plus u del u del x. This is another form we can write explicitly u del u del x, v del u del y plus w. That means splitting up the total derivative or substantial derivative in terms of temporal and convective. That means explicitly showing the acceleration in its components, temporal and convective, is equal to xx minus 1 upon rho del p del x. So any one of this is the x component equation of motion. Similarly, this is del v del t, the temporal acceleration, plus the convective acceleration del v del x associated with u, del v del y associated with v. This you know earlier, w del v del z from the kinematics is equal to xy minus 1 upon rho del p del y. So this is the y direction motion, equation of motion in y direction, and this will be del w del t plus u del w del x plus v del w del y, well, plus w del w del z is equal to xz minus 1 upon rho del p del z. So therefore we see this is the z direction. So this is x direction equation of motion, rather x small y direction and z direction, and these three sets of equation, this and this, or this and this, they constitute the Euler's equation. This is known as Euler's equations in the, that is the Euler's equation, O-E-U-L-E-R-S, the scientist, big scientist, Euler's equation. Euler's equation or equations are the equations of motions for the flow of an ideal fluid. That means it is the conservation of momentum for the flow of an ideal fluid. Now you see that by the method of induction, as we did in case of continuity equation, these three equations can be put in a vector form. Can anybody tell what is the vector form? These three equations, du dt xx minus 1 upon rho del p del x, dv dt is xy minus corresponding gradient, it is the y component del p del y, it is the z component del p del z, and the body force z component, this is the y component of the body force per unit mass, this is the x component of the body force, and gradient with respect to x direction. So can you tell this can be written like that, d of dv dt, where v is the vector, is equal to x minus gradient of p, grad p. This is the vector form. Why? V is given by its three scalar components in three coordinate directions. Well, any problem? 1 by rho, very good. Always I am missing something. Which side? Very good, grad p by rho. Very good, very good. So I am happy that today you are very careful. K, x, z and grad p just by the simple preliminary vector, the gradient of a scalar field is just their gradient in the respective coordinate direction. So it is the definition of, please, any other thing, this is all right. So therefore this is the definition, or this is the vector form of the Euler. dv dt is equal to x bar minus grad p by rho, or somebody, some book or somewhere they write rho here. dv dt is x bar by rho minus grad, sorry, x bar into rho minus grad p. Rho, sorry, rho x bar into grad p. This is another way. Doesn't matter. Here, this is the acceleration, physical significance you see. As you that define the equation of motion, each and every term is the force. This is the acceleration. That means force per unit mass. This is the negative of the inertia force per unit mass. This is the body force per unit mass, and this is the pressure force per unit mass. If you write in this way, rho dv dt is the acceleration time the density. That means inertia force per unit volume, negative of that, because inertia force defined with a negative sign, and this is the body force per unit volume, and this is the pressure force per unit volume. Only the units are different. Any one of the two ways we can express. So this is precisely the Euler equation of motion in a vector form. So why I am writing in the vector form? Again, similar to continuity equation, if I have to derive the Euler's equation of motion in a different frame of reference, not in a Cartesian frame of reference like x, y, z, rather if we have to define it in a cylindrical polar coordinate system or spherical polar coordinate system, one way is to follow the mathematical approach. That means you have to write this thing in the corresponding, so V will be all right, V bar, it will be defined with its scalar components in the respective coordinate axis. So only thing is that the grad P has to be expressed in terms of the respective coordinates. For example, if we think of a cylindrical coordinate system, for example, this is x, this is y, that means a r theta and this z coordinate, then we define V as I Vr plus j V theta plus k Vz with the Vr V theta Vz with the r theta z component velocity and I j k are the unit vectors along that. So what is the grad P in that case? I del P del r plus j 1 upon r del P del theta plus k, this probably you know, del P del z. So therefore one can write this dV dt is equal to what? X minus grad P by rho. Now if I write the r component, what will be this? dVr dt is equal to xr. If I define xr is the body force per unit mass in r direction, minus 1 upon rho del P del r. Is it all right? Can anybody tell, is it all right? I have written the equation with a gap. Yes sir. Is it all right? What is that? There will be another component, that is the beauty, that is V theta square by r. Because of the V theta, I told you earlier, there is an inward radial acceleration. That means in the negative r direction. So minus V theta square by r is the acceleration because of V theta. That component comes. So even if you follow this ddt, so when you convert the total differential with the curvature of the, in consideration of the curvature of the coordinate system, mathematically also you arrive to this. So you better write dVr dt as the total change in the, when you make a vector transformation. Some of you may be very strong in mathematics, you can do it, but you can follow this way also without going for that mathematical complication. When you make the dV dt scalar component in r direction, it will be the total differential of Vr with respect to t with an additional term. So it comes from the mathematics considering the curvature of the coordinate system. But one can think in a physical way also that it is the rate of change of radial velocity with time, it is the radial acceleration and acceleration in the radial direction along with another radial acceleration which arises solely from the tangential velocity. That means in a flow field where radial velocity is 0, having only tangential velocity, there also a radial acceleration is there. This is known as centripetal acceleration, as you have already seen. So similarly, in theta direction, it will be dV theta dt plus Vr V theta by r is equal to x theta minus 1 upon rho del P del theta. And similarly, dVz dt, there only dVz dt. Z direction acceleration is responsible for the change of Vz, z component of velocity with time, xz minus. All right, please. Okay. Now, these three equations, this one and this one, this is r direction, this is theta direction and this is z direction, can also be derived by a similar fashion, that is by taking a control volume appropriate to r theta z coordinate and making its force balance and equating it with the mass time acceleration according to Newton's second law of motion. All right, thank you.